what are these AI systems doing today? Because I think a lot of times people are using various AI models without necessarily realizing it.
Right.
Often these features feel pretty magical, but they're actually, often powered by these machine learning models. Lots of data about some of these, problems or domains,
right,
but we don't necessarily have the deep understanding to make sense of that data. And so this is where sometimes neural networks, which can learn, fairly complex patterns from data, can actually be useful and can create new insights or create new capabilities that didn't exist before.
Hi friends and fellows, welcome to this special series of conversations involving personalities coming from a number of campuses, including Stanford University. The purpose of this series is really to unleash thought-provoking ideas that I think would be of tremendous value to you. I want to thank you for your support so far, and welcome to this special series.
Hi, we're honored to have Jeff Dean, who's the chief scientist at Google. Jeff, thank you so much for coming on to our show, Endgame.
Thank you for having me.
You've been at Google for a very long time. You're employee number 29 point something. I want to ask you about how you grew up. You were born in Hawaii, and tell us about how you grew up and how you got interested in computers and how you've transformed Google into what it is today.
Sure. Yeah.
That's a loaded question, but we'll start off with your childhood.
Yeah. I mean, I think I had a somewhat interesting childhood in that my dad did tropical disease research for the first part of my childhood and then switched to being a public health epidemiologist. And my mom did medical anthropology. And so they somehow like to move a lot. I'm an only child. So every so often we would move. I went to 11 schools in 12 years. Oh. And so I, was born in Hawaii, then we moved to Boston and then Uganda and Boston and Arkansas and Hawaii and Minnesota and Somalia and Minnesota and Atlanta for the last 2 years of high school. And then I went back to Minnesota for college. And then I ended up working for the World Health Organization in Geneva for a year and a half before going to grad school in Seattle. And then I came to the Bay Area and I haven't moved since. My kids did not get the same tour of the world that I did, but it was interesting because, seeing a lot of different environments and a lot of different schools and a lot of different ways of teaching and so on, it was, different than many people's upbringing. Was
there a time when, or a few times when you were pushed or tempted as to pursue medicine, the area of expertise of both your parents?
Yeah. I mean, I think I have had an interest in not as a doctor, but as obviously conversations around the table growing up were always about, public health often. Yeah. My dad actually, the way I got into computing, which is something you asked, was my dad was always interested in how could you use, better information to help make better public health decisions. And so he, was kind of frustrated at the time. This was kind of the mid to late 70s, where mostly people didn't get to use computers themselves. There was a big mainframe in the basement of something, and you would go tell some programmer, no, this was actually in Hawaii.
Okay.
And, you would go tell someone what you wanted the computer to do, and they would do it. And then you would not have this nice kind of more natural interactive experience with computing that has come to pass with personal computing. But my dad saw an ad in the back of a magazine for solder it together yourself kind of kit computer called an IMSI 8080 that when I was, I guess I was 9. So he bought one of these and I was probably not much help, but I held the soldering iron a little bit and helped him solder it together. It didn't do much at first because it was really it didn't have a keyboard or a screen. Really, you could toggle together toggle in individual bits and then like enter them into memory, and you could get little programs going that way. Then we got a keyboard. That was a huge improvement. So you could actually type, actual characters and so on. But I kind of got interested in that as we got a couple more peripherals. You could start to type in computer games in BASIC. So you type in the source code of a game. There was a book I got with source code for a whole bunch of different games, and you could type it in and then you could play the game. And then I started to get interested in, modifying the game a little. Like, it was a good way for, I think, young kids to get interested in programming, is have something they want the computer to do. And it's kind of very motivating because you can kind of then figure it out on your own, or like, how would I make the torpedoes go twice as fast in this game or whatever. So that was my introduction to computing. And then we were actually quite fortunate to move to Minnesota, which at the time had a interactive time-sharing system for all the middle schools and high schools in the state. And so every school got a computer account and some computing hardware to dial into this centralized system. And actually they had kind of these interactive chat rooms at the time. So it was sort of like what the internet has become, but 20 years before that. And so kids in Minnesota were living the internet dream earlier than most.
Then you moved on to Seattle for your graduate studies, right? Yes. After Minnesota.
Yeah.
Why Seattle?
Well, my wife and I were applying to graduate schools together, and the complexity of matching programs that were good in her field and my field. University of Washington was an awesome pick for us. We love Seattle. A little gray sometimes, and rainy. Little rainy. My Hawaiian upbringing is, kind of spoils the weather for most other places, but Seattle was great. I really liked my time in graduate school there, and I learned a ton, and then I came to the Bay Area.
Now, what made you join Google in 1999?
Yeah, so I'd actually come down to the Bay Area to work for Digital Equipment Corporation, a small research lab in downtown Palo Alto. And actually, that was the lab that created AltaVista, which was an early search engine. So some of my colleagues there did the early sort of key work on that system. And AltaVista, at the time had a much larger index than most people. It was a very fast responding system. And one of my colleagues had put together from the crawled pages in the AltaVista index, a system where you could actually, in sort of programmatic form, see what pages point to which other pages, which is not so hard because you could just look at the contents of the page, but also what pages point to each page. So going backwards in some sense. And so you could navigate this sort of computational graph forwards and backwards with this kind of set of API calls. And that proved to be quite interesting. So a colleague, Monica Hensinger, and I were working on how could you find related pages to any given web page in the web. And we thought we'd have to try fairly complicated things, but we said, let's just try something really simple first, which is let's look at a page and let's look at what pages point to that page. And then what other pages do they point to? And then you just do some counting and frequent things, and then you divide by to normalize the probabilities. And all of a sudden, from the Washington Post, you'd get a list of like CNN and the Wall Street Journal and New York Times, or some page about hiking in the Bay Area. You'd get a bunch of other pages about hiking in the Bay Area.
Wow! And
that caused me to think, there's actually a lot of information in the link structure of the web. And ultimately I decided I wanted to be at a smaller company than it was actually, a little challenging sometimes to get research you'd done out into the world through a very big company. I found it was just a little indirect. And so I decided I would come to Google. I knew
a small company.
Yeah. We were all wedged. Actually, all of us were wedged in this tiny little area above what's now a T-Mobile store in downtown Palo Alto when I started. But I knew Oris Hutzla, who's one of our earlier employees. I knew he'd come here. He and I were he's my academic uncle, I guess.
Wow.
And so I had, chatted with him many times at different compiler conferences because we both had a background in compilers and program optimization.
When did you get the sense that Google was going to be as big as it is today? Did you think like that already in 1999?
Yeah, I mean, we clearly at that time had a really successful and growing service, and you could see it. Like the whole company could see that, like our traffic was growing. 6, 7, 10% a week at times, and if you do 1.1 to the 52nd, that's a huge amount of growth in a year.
Yeah.
And a lot of the first couple of years were really, how can we avoid melting every Tuesday at peak traffic time? So, there was a whole bunch of work of deploying new hardware, but that wasn't enough. We had to do, software performance optimization. We had to sort of redesign the system because often when you have software that works at scale X, it suddenly doesn't work at scale 10x or 50x. And so you're constantly refiguring out, how are we going to, redesign this part of the system because now it's a big problem, whereas it didn't used to be.
So when was it that you realized that this was going to be this big? One
of our early employees, we actually had a giant wall, a really long wall, and he put up a butcher paper kind of chart on the wall, and it was called the crayon chart because every day he would plot like, how many queries did we get on Wednesday?
Probably like this.
In different colors, we had different partners. And then, you would go along a bit and then he would run out of room at the top of the paper.
Oh my.
So he'd have to scale it down by a factor of 5 and then start over again. And it would grow again to the top of the paper. And then he would scale it down by another factor of 5. And so he did many, many scalings. And, we went from, very few queries per day when I started to, a lot more queries. And then obviously expanded into a bunch of other product areas and things like that. So.
And anything that you think could have been done differently since the start of Google?
Oh, so many things.
Okay.
I mean, I think it's always good to reflect on, what are we doing well, but also what could we do better? I mean, I think one lesson that sticks out is, whenever an organization is growing quickly, we were also hiring people pretty quickly. And I feel like every kind of doubling in company size caused something that used to work well to no longer work. And there's kind of like these leaps of change that cause that. Sometimes it's you were all on one floor and now you're on multiple floors in the same building. And then sometimes you go to multiple buildings. And then all of a sudden, instead of all of your engineering being done in Mountain View, we opened a New York office and a office in Zurich. Now we have to figure out, okay, how do you have people in many different locations working together? And this was before, obviously all the technology we have today of video chatting and that kind of thing. It was, more challenging to figure out who should do what, who is doing what. But we worked through that. We had about 5 engineering locations for a while. One period that I think we could have done a little better is we decided we would greatly expand the number of engineering locations we had. So we went from about 5 to 30 in a couple of years. And really that was about hiring great people who in different places who didn't necessarily want to move to one of our locations, but we're like, oh yeah, that person and this team of 5 people, we should start an office around them. And it's really, it took a while to digest of how should we work in 30 engineering locations instead of 5, because each one of these small locations would kind of look at the main engineering centers in New York and Mountain View and say, we should do stuff just like they do, which means work on everything. And I think that doesn't really work if you're working on everything, but you're 15 people.
Yes.
So we tried to create a little bit of specialty and focus in some of these centers where they get to work on, really prominent, important things, but on like just a handful of the different products we have. And,
You know, you started studying neural network in 1990. We've been talking about that, right? Mm-hmm. And at that time, it was hugely inhibited by the lack of computational power.
Yeah.
Do you see the computational power having grown as exponentially as you would have thought then today?
Yeah. I mean, I got introduced to neural networks in my senior year as an undergraduate, and
right.
It was kind of a 1-week module in some class I took, but I was very intrigued by them. It seemed like kind of the right abstraction.
Yeah.
And so I decided to then work with that faculty member to do an undergraduate research project, undergraduate honors thesis on, I felt like we just needed more computation. So maybe we could do parallel training of neural networks. So we could get the sort of 32 processor machine in the department training a single neural network rather than, just using one processor.
Yeah.
I was convinced if we could use 32 times as much computational power, it'd be amazing. Oh, it'd be so great. Turns out I was wrong.
Yeah.
We needed like
you kept saying 1 million times.
Yeah, 1 million times as much computational power, which is sort of what the progress in general computation produced over 20 years or so. And then, through just general improvements in computer architecture, improvements in semiconductor manufacturing processes and fabrication shrinks and so on.
Yeah.
All of that, compounded to the fact that our phones now are, 100 times or 1,000 times as powerful as the giant desktop machines we used to use. So I feel like once we started to have about 1 million times as much computational power in maybe like 2008, 2009, 2010, then it started to be the case that neural networks could solve real problems, not just kind of interesting small scale toy problems almost, but they could actually start being applied to real problems in computer vision and in speech recognition was like some of the earlier areas we started to look at. And then, various kinds of language tasks, could they understand words in a way that was different than the surface form of the word, but really in what context does this kind of word make sense? And are there other words that are similar to that? And, what is the past tense of this word? And can you, really understand language more deeply than it's just a sequence of characters?
How do you see the evolution of the TPUs going forward? Is it going to get much more exponential than what we might have seen in the last decade or two?
Yeah, I mean, I think...
We're at what, TPU... V4 now? Or
we've just announced our V5.
V5, okay.
Through our Cloud TPU program.
Okay.
So we've been building specialized hardware for machine learning and in particular neural networks now for, quite a while. I think our first TPU V1 was discussed in 2015.
Right.
But really it's about one of the nice properties that neural networks have is that they're sort of all described by different sequences of kind of linear algebra style operations, different kinds of matrix multiplies or vector operations. And that's a very restricted set of things you need the computer to do. It's not like you need it to do all kinds of different things like general purpose computing could. And so general purpose CPUs are great for running your word processor, but they're not exactly what you want for running machine learning computations because they're too general. That generality costs you performance. And instead, if you build hardware that is very specialized to, exactly what the kinds of computations neural networks embody, you will be able to, get huge performance improvements, better performance per watt, better performance per dollar, performance per overall chip. And the other property that neural networks have is, unlike a lot of kind of traditional scientific computing where you need actually a fair amount of precision, they're actually very tolerant of reduced precision arithmetic. So you could do computations in 8-bit integer format or 16-bit floating point format, unlike 32 or 64-bit floating point format, which is typically used for weather simulation code or whatever. And that means you can squeeze more multipliers into the same chip area and get higher performance.
Okay. You've talked quite frequently about some of the constraints with respect to the neural network. the modalities, multitasking versus single tasking, and sparsity versus density.
Yeah.
Talk about those.
Sure. Neural networks are sort of loosely inspired by how real biological neurons work.
Right.
In that the individual unit in a artificial neural network is something that takes in some inputs,
right,
and then has weights on those inputs. How important does it think this input is versus that one?
Yeah.
And importantly, those weights are learned through a learning process. And then the neuron takes all that input and then decides.
The artificial neuron.
Right. And loosely inspired by what real neurons do, is it decides what output it should produce. Should it fire in some sense, or should it produce nothing?
Right.
And how strongly should it fire? And so that's really what a neural network is it's composed of a whole bunch of these individual artificial neurons, all typically arranged in layers. So you have, the lowest layers that take in very raw forms of data, be it, pixels, a small patch of pixels of an image, or a little bit of audio data in, audio form, or, a few characters of textual input. And then they sort of build interesting features. Let's discuss images, because I think that's like a very, easy way to think about the kinds of features that get built up through this learning process. So the lowest level features tend to learn very simple things like, is there a line at this orientation in this part of the image, or this orientation, or is it like mostly gray, or is it mostly red, or is it like, a different color?
Right.
And so different neurons will get excited when they see different patterns. Like this one gets really excited. It's like bright red. Wow, exciting. And this one has a line like this. And so as you move up the layers, what's happening is these neurons are taking input from the lower level ones, and they're learning kind of more interesting and intricate patterns that are based on combinations of the features that cause these lower layer neurons to get excited. So like now it's like, oh, it's red and it's got a line through it like this. That's really exciting. Or it's got an edge with red mostly on one side and not on the other.
Right.
And as you move up farther and farther, the features become more and more complex. So you might have something that's got like something that looks like a wheel, or something that looks like a nose, or an eyebrow, or things like that. And even higher, you get sort of fully featured things like, oh yeah, this one fires when there's a car with a front-on view of the car, or something like that. And I think that kind of process happens because typically you are training the neural network. There's a lot of different ways of training it, but one of the simplest is what's called supervised learning, where you have some, say, image data, and then you have labels associated with those images. You say, okay, that one's a car, that one's a cheetah, that one's a tree.
Right.
And so the output of the model at the top level is trying to predict which of these many different categories of images is it. And the way the training process works is you make a pass upwards through the model, forward pass it's called, and you see what the model predicts.
Yeah.
And it says, okay, well that looks like a tower. But maybe it's really a tree. And so what you can do is then make little teeny adjustments to all the weights in the model so that it is more likely when it sees this image or a similar image to say, give the right answer, to say it's a tree, actually, not a tower. And the training process is just repetition of that observing of real data and what it should be, and then producing, adjustments to the weights of the model.
How do you make sure that you can actually weed out this seeming bias by way of the weaker ones get weeded out, and then the stronger ones or influences get promoted? That just sounds like an inherent bias
in the way individual neurons.
Correct.
Yeah, I think what actually tends to happen is different neurons will latch on to different kinds of patterns. And some of those patterns are irrelevant for any particular image. Like if it's a image of the outdoorsy scenes, all the things that detect vehicle parts are kind of mute. Like they don't actually produce large outputs. But all the things that are about, foliage and green and trunks of trees and so on are like very exciting.
Yeah.
And so I think, part of training a neural network is you want this diversity of different kinds of patterns that the model can learn. And also you need the model to have enough capacity, enough, neurons and parameters that it can absorb and learn from the data that you're exposing it to. Like if you have only 5 neurons and you give it 1 million images, it's not going to do very well to generalize to new examples. I mean, that's really one of the things in machine learning you're trying to do is learn from representative data, but not just completely remember exactly what that data was, because you want to learn when you're confronted with a new image or a new piece of text to generalize to those examples.
How optimistic are you with respect to being able to basically address these 3 concerns or constraints with respect to modality, density, and single tasking?
Yeah, I mean, I think I'm...
Or how soon do you think those are going to get optimally remedied by way of the exponential growth in TPU capabilities?
Yeah, I mean, I think we're making a lot of progress on them. So we're actually pretty far along at generalizing some models that are previously mostly text only or sort of code, software code kind of like into models that can actually understand, text, code, audio input, image inputs. And so that I think is starting to be well understood through research my colleagues and others in the community have been doing over the last 3 or 4 or 5 years. I think in terms of multitask capability, one of the things we're seeing with these models that are trained on, large corpora of general text or images and text or whatever, is that gives them the ability to actually generalize quite well to new things you ask them to do. Like you say, okay, can you draft me a letter to my veterinarian about my dog? The dog is not feeling well. And, the model has never seen exactly that requirement or request, but it is able to sort of understand what it is you want and to produce, plausible sounding text that actually fulfills that person's need. And you're starting to see not just generalizing from one data example to another in the same kind of overall category. Like 10 years ago, the generalization you wanted was take an image and be able to predict which category it's in from having trained on a bunch of images and those categories. Now you're seeing the ability to generalize across tasks in some sense, like asking the model to do something it's never been asked to do, but is kind of close enough to things it knows how to do, and it is able to generalize. And then the third one is sparsity. So most machine learning models these days are dense, which means you have all these neurons, artificial neurons, and the entire model is kind of activated for every example or every input. And there's a form of model that we've done a fair amount of work in called sparse models, where you actually have different pieces of the model, and the model can turn on and off different pieces and can actually learn which pieces are most relevant for which kinds of inputs. So you might have some inputs that are about Shakespeare. And so maybe there's a part that's really good at kind of Shakespeare-y stuff, but the part that knows about C++ code or Java programming is probably not active there. And there's another part that is really good at identifying garbage trucks in visual images. That's probably not active either. But you want this model to have a lot of capacity. So it's got a lot of pieces of it that it can call on, but it doesn't need to call on all of them for everything. And that creates a much more efficient model because now instead of activating the whole model, you're maybe activating 5% of it. And that makes it much more energy efficient. but you still have this capacity to remember a lot of stuff.
It's probably not going to be too far in the future, right? When you think you're going to be able to address these constraints.
Oh yeah, like I think the multimodality stuff, we've already seen a bunch of work from Google Research and Google DeepMind on multimodal models of various kinds, that can take in, visual inputs and language and answer questions in text form, or that can generate, we've seen a lot of work on generating images or generating audio from various kinds of other inputs. Like, can you take a text prompt and generate an image? And those models for that have been improving steadily. You now can take text plus an image and say, okay, generate me a picture of, a giant castle with this dog in front of it. Right? Like, it's cool that it can generate a picture of a castle with a dog in front of it, but often what you really want is your dog in front of the castle.
You've recently or some time ago gave a lecture or a talk in front of quite a bunch of computer science students or experts. You talked about the 5 trends with respect to machine learning: general purpose, efficiency, benefit to society, community, and people, benefit to engineering, science, and health, and broader and deeper. Talk about those.
Sure. Yeah. I mean, I think, the first part was about these trends of improving, the multimodalities, capabilities of these models and sparsity and so on, and the underlying hardware and systems we use to train them getting more capable. The second part, it was about, or another part of the talk was about, what are these AI systems doing today? Because I think a lot of times people are using various AI models without necessarily realizing it. So on, for example, the Android phone, there's a lot of capabilities in that phone that are powered by various kinds of models. So it can like screen your calls for you, and it can, you can say, I don't want to pick up my phone yet. I just want to like understand what it is this person wants. And then it can relay a transcript of what they said. They say, oh, this is, hi, I'm Fred. I've got a delivery for you at the front door or whatever. Or that can, on the phone, do various kinds of computational photography techniques to enhance the images, to be able to remove, that annoying, unsightly telephone pole in the background when you took your photo, or a variety of other things. And I think, often these features feel pretty magical, but they're actually, often powered by these machine learning models. And then another part was about how AI and machine learning is really accelerating a lot of aspects of scientific discovery. I think one of the things that, particularly in fields where there's a fair amount of data and you're trying to like pick up on complicated patterns that are not well understood, genetics or healthcare or various kinds of weather prediction. A lot of these things have the property that there is lots of data about some of these, problems or domains, but we don't necessarily have the deep understanding to make sense of that data. And so this is where sometimes neural networks, which can learn, fairly complex patterns from data, can actually be useful and can create new insights or create new capabilities that didn't exist before. Weather is maybe I can use weather prediction as a good example. So traditional numerical weather forecasting has like a set of physics-based equations about how the weather and the wind and the atmosphere interact in order to make predictions of like what's the on the ground weather going to be like 12 hours from now, 3 days from now. And that's great, but those simplified equations probably leave out a lot of things that we don't fully understand. And so when you actually try to apply neural networks to weather forecasting, you approach the problem very differently. You actually have a fair amount of historical data about the weather conditions 4 days ago were this, and now, 3.5 days ago, they're this. Or, even 3 years and 1 day ago, they were this, and now 3 years ago, they were this. And this sort of gives you the ground truth of what your model should predict. So given the weather 1,000 days ago, can you predict the weather 999 days ago? And that actually turns out to be a fairly successful approach for weather prediction. And you have kind of ample amounts of data to train on. And then you want to generalize to, new weather situations you've never seen before, and also to the future. So
how soon do you think we're going to be able to, I mean, machine learning has done so much, so well, so fast with respect to reading text, understanding to some extent, then audio, then visuals, all kinds of visuals, right?
Yeah.
What about smell?
So we actually have done some research.
I mean, temperature, you can do that right already.
So within Google Research, we've done some work in this space starting about 4 or 5 years ago.
Right.
And it turns out that with there's various kinds of instruments that can sense the olfactory characteristics of the air,
right,
and can give you very raw data about what things are hanging in the air. But it's hard to really then put high level labels on that. So in the same way, you have the pixels of an image, and you can train a neural network to say, okay, well, when I see that kind of thing, that's a leopard. You can do the same thing with these olfactory signals to say, okay, that's a lot like lemon with a hint of pine needles or something. And this actually works.
Okay.
The actual device that gathers the data is still a little big, so it's not like a portable thing you can put in a cell phone yet, but it turns out this is an important problem for a variety of reasons. One is there's actually a lot of, some industries that want to create particular scents, and they want to be able to, understand a scent, but also do the reverse, create a scent. Like in the same way you want to, you've seen these image models where you can say, please give me a dog in front of a castle. You'd like to say, please give me what I would need to mix together to make a scent of,
of a woman,
goulash and cinnamon or something. And so that's one application, is for perfume industries or consumer packaged goods. But another one is potentially in healthcare related things. There's some evidence that dogs, which have particularly sensitive noses, can actually, pick up on subtle signs of cancer in some cases. And so that indicates that maybe there's signal in these olfactory raw data that could actually be used for health purposes.
Anything else that we should anticipate in terms of what could be cool about what ML could be doing to humanity?
Oh yeah, I mean, I think I'm pretty optimistic about a bunch of different application domains. I mean, I think one is in the area of education.
Right.
So we're not quite there yet, but it's close to being able to say, "Can you please tutor me on this?"
Wow.
You take in a chapter of a textbook, and you can imagine a system that absorbs that chapter, or maybe multiple chapters from different books, and then asks you questions, assesses the correctness of what you answered, identifies areas where you could use more more depth, and asks you more questions about that kind of thing, fewer questions about stuff that you seem to already know pretty well. So imagine being able to do that for anything you want to learn, like either as a kid in school, or as an adult.
Or English. Language.
Yeah, English is great. There's all kinds of interesting language learning applications. I think you might be able to create really interesting dialogues that help people learn language, and they're going to be more interesting than the kind of pre-crafted, fairly rudimentary things. Like you could say, I want to learn English, and I want to talk about, hiking in the forest or something today or whatever. And it could probably, help you achieve those two objectives, a pleasant conversation about hiking and you're learning English at the same time.
I come from a region, it's called Southeast Asia. And it kind of gets, it's a bit under narrated. people here in Silicon Valley tend to talk about other places around the world as opposed to Southeast Asia.
Yeah.
And I think part of the structural problem with that is we just don't speak English. Not enough of us.
Yeah.
I mean, Singaporeans, all of them speak English.
Yeah.
Good chunk of the Filipinos, they speak, but the rest of Southeast Asia.
Mm-hmm.
So if we would have had this conversation 5 years ago, I would have been a lot more pessimistic about the future where we could actually communicate with the international community. Now, with the advent of ML or AI and all that stuff, I'm a lot more optimistic about getting 100 million people in Indonesia to be able to speak English, maybe 400 million people in Southeast Asia out of the total population of 700 million people to be able to speak English.
Yeah.
It's a breakthrough.
Yeah,
it's life-changing.
Yeah, enabling people to communicate with each other, I think, is a hugely impactful thing.
Yeah,
and whether that's through teaching people to learn a second or a third language, or whether it's enabling people who don't speak the same language to communicate effectively. We have some of our products like Google Translate can actually, you put the phone on the table and you're speaking one language and I'm speaking another, we'll actually produce transcribed versions of what we're saying. And we also have versions that can transliterate it into actual audio in people's ears. And I think that's, a really important capability, because the more we're able to communicate as all people, the better it is. And it's also something where machine learning can actually really help, because we've seen just dramatic improvements in the capabilities of the quality of translations through these larger neural network based models, as well as speech recognition and speech production for not just 5 or 10 languages, but actually for 100 languages. Google Translate supports more than 100 languages today, which I think is really important. We actually have an ambitious goal to support 1,000 languages in our products, and this is sort of a
we have 700 of those in just one country, in Indonesia.
Yeah.
We call them dialects.
Yeah. So 1,000 languages is not. I think there's something like 7,000 spoken languages in the world, and 1,000 covering the top 1,000 would be amazing.
Yeah.
Even the top 100 covers a lot, but there's still in the next 900. There's a lot of speakers who are sort of left out if we don't support those languages, and so we definitely want to do that.
I want to talk to you about sustainability.
Okay.
And I'll draw the picture in terms of how things are a little bit different in developing countries, right? I mean, I've been saying the narrative of sustainability is elitist because it resonates to about 15% of the population of the world, whereas the 85%, they're a lot more worried about putting food on the table.
Right. Yeah.
And they don't mind stopping, using coal today, as long as the alternatives are affordable.
Yeah.
Technologically, alternatives are available, but economically, they're just not affordable for most people on the planet.
Right. Yeah.
What do you think Google or you as a scientist could be thinking about? What can be done to bridge the gap between the narrative of sustainability and the narrative of development? Because I think it's important for the planet to be collective about this, right? In terms of attaining carbon neutrality by 2050 or 60.
Yeah.
There just seems to be no realism when we hear the rhetoric of attaining carbon neutrality by 2050 at the rate that we're seeing a bunch of these people here that just can't afford it. The technologies. And I'm sure you got a lot of smart people here in this building that can figure out how to make things a lot cheaper economically by way of technological innovation that's been very exponential.
Yeah, I think this is clearly a planet-wide issue, right? And we all need to be working together on this.
Yeah.
And it is definitely the case that the more economically developed countries have produced way more emissions in the history.
We don't have to get there.
Yeah. But, I think there are a few sort of positive signs. So one is the cost of renewable energy, like solar panels have been kind of on a, dramatically improving curve, a bit like computation was, 15 years ago. We're now seeing
still high though.
Still high. Battery technology is improving a lot. And so the combination of solar and battery plus wind is becoming much more affordable. In fact, in many parts of the world, I think if you look to install new power capacity, that actually becomes the economically rational choice. So that's a good thing, because I think one of the issues we've had is in the world is just there's things that are not factored into people's decisions. Like, if I install another coal plant, it's cheaper for me, even if that necessarily causes indirect emissions that impact everyone. So we've been looking at what are things that we can do to improve sustainability and reduce emissions with technological solutions. Right. So one of them is a project called Greenlight, where basically by using traffic patterns that we can observe through Google Maps, we can actually identify ways in which cities around the world can make improvements to their traffic infrastructure, to signals and so on, to actually reduce idle time at intersections. That's actually a major source of emissions, is just cars not going anywhere. It's also a situation where people don't really like not going anywhere. You're in your car to go somewhere. And the emissions from the idling engines actually are pretty harmful. And so with Greenlight, we can actually make suggestions to different cities all around the world and have them adjust the stoplight timing. Most stoplights in the world have fairly simplistic methods. It's sort of like, is it rush hour or not, is kind of the level of sophistication in many of them. But now we can actually say, okay, Tuesdays between 10:37 and 11:30, you should set the signal timing to 42 seconds instead of 35, and you'll get way more throughput on your roads. 90% reduction in the number of people who need to wait through a second light cycle, for example. And so we've actually got pilots going with 12 cities all around the world. I think it's on 4 or 5 continents, and Jakarta is one of them. And so we're actually seeing quite positive results from that. And we're sort of learning from that early experience, partnering with those cities and trying to sort of expand that program. But that, has rolled out much more broadly, would have a huge potential impact on reducing emissions, and it also would help people by getting them where they want to go faster, which is also a nice side benefit. Another area where I'll talk about is contrails. So the sort of long linear clouds you see behind airplanes sometimes. Turns out those are actually quite harmful for carbon emissions, because they trap in heat at certain times of the day. And actually, the contrails produced by airliners are roughly 1/3 of the total contribution to warming of the aviation industry.
No kidding.
The entire aviation industry, kind of surprising, but
1/3 of the actual burning of carbon.
1/3 of the overall footprint of the aviation industry is related to contrails. We've actually been doing, but contrails are actually avoidable. So if you're a plane and you're flying, and the conditions at this altitude would actually produce contrails at a time when that's a bad idea, because the conditions seem like that contrail would be harmful, you can actually change your altitude, or with going up or down a little bit, you can actually get to a situation where you won't create a contrail, because it's really just the exact temperature and ice crystal formation that, it's really just ice crystals forming around sort of soot from the exhaust of the plane that causes contrails. And so we've actually partnered with American Airlines to do a controlled study where we took, I forget exactly how many, about 100 flights, and we took 50 of them, and we gave them commands about, where we thought contrails would be produced and whether they should go up or down on their flight path. And what we saw was a 50% reduction in contrails for the flights where we were controlling that versus the ones where we did not.
And how are you actually controlling?
So we control it by saying, okay, flight, American Airlines flight operations would tell them to go up to
at a certain
31,000 feet instead of 30,000 feet or something. And then actually it's kind of cool how we closed the loop and figured this out. So now you have all these flights. And so we use real-time satellite imagery of when the flights occurred and the paths they took. And then you can use computer vision to detect, was there a contrail produced by this flight versus this one?
If you take a look at some of the publications by experts in energy, the demand for fossil from automotive is going to continue declining, right? But demand for fossil from aviation is going to go up.
Yeah, and so this
you just can't electrify airplanes that fly long haul.
Yeah, this approach seems like it might reduce about half of the warming related to contrails, which is a third of the overall impact of the industry. So that might be like a sixth of the aviation industry impact.
What about food security? I mean, there's a lot that can be done technologically or scientifically, right, to improve upon a pre-existing convention.
Yeah, absolutely. I mean, I think that has a very broad set of ways that you can approach improving that situation. So one is just helping farmers understand their crops and, is this I'm getting these weird patterns on my leaves of this particular crop. Is that a disease I should worry about, or is it fine?
Yep.
And computer vision models can actually be helpful with this. We've done some deployments with other nonprofits working in, I think it was Kenya or Tanzania, helping understand cassava leaf, images and helping tell cassava farmers, is this a disease they should worry about? And if so, how should they treat it? Another is just predicting where food insecurity is likely to occur, because we know, when you already wait until a population is in crisis, it's actually kind of late at that point. You'd rather give sort of assistance to people that are not yet in crisis so that they can sort of, plant more crops or do things that help them avert the most dire situations. And using machine learning to help make predictions there is something that we're partnering actually with. Google Research is partnering with the FAO organization to sort of help with that prediction.
Let's talk about AI.
Okay.
Convince us that it's going to lead up to a good future.
Yeah. I mean, I think obviously there's a lot of discussion around this.
Let me just, put some context to this.
Sure.
There is a sense, at least from a layman like me, that it's not being pushed forward in an adequately multidisciplinary manner. Mm-hmm. It just seems highly technological, right? Without roping in those people that are expert in culture, economics, environment, spirituality, philosophy, and all that good stuff. I just think that those are important, right?
Yeah.
To make sure that this goes to the end of the pipe in a benign or judicious or wise manner, right?
Yeah, I definitely agree with that. I mean, I think one of the things you want to do whenever you're thinking about applying technology to some, problem is you want to bring in people who have a lot of knowledge about that area,
right,
and work with them. Some of the most interesting projects I've worked on are ones where, I might have some technical expertise, but where I learn a lot from colleagues who have other domain expertise. They're clinicians and they understand this kind of healthcare problem extremely well. And they can say, if we could do this, that would be really helpful. This isn't that helpful. This is a big problem. This is not a big problem. We should look out for that. So whenever we're approaching, the use of AI and machine learning in different domains, we want to bring in, that comprehensive set of people who are thinking about, that domain, who are thinking about, issues of representation and fairness.
Right.
If it's, technology is going to affect, people in one community, you want people who are from that community or who speak that language or, understand the situation in, that city or that country more deeply so that they can provide feedback and advice and work together to improve things. This is one of the things that Google has done as we sort of saw more use of AI in our products and, thinking about it in terms of, where was it going to be applied in other areas. We actually put together a set of principles by which we think about, how do we make sure that we're responsible in thinking about how AI is applied to different problems. We want to avoid creating unfair bias. We want to avoid creating harm. We want to sort of focus on, positive use cases. And our AI principles, which we published in 2018, have a set of 7 principles by which we think about these, and we evaluate downstream uses of machine learning and AI in terms of those principles. And I think it's actually been a helpful thing for us to put those out externally.
Yeah.
Because, we'd been thinking about AI for a while, but other organizations were starting to think about using machine learning or AI in, their, whatever environment, whatever problem they're engaged in their discipline or their domain. And I think it was helpful for us to put out those principles so other people could, or other organizations could reflect on them, say, yeah, that makes a lot of sense. Or, in our industry, this one doesn't necessarily make as much sense, but these other ones resonate.
How do you make sure that you're going to be able to find the right balance between humanity and profitability?
Yeah, it's tricky. I mean, I think we actually do a fair amount of work that we don't worry too much about. Is this going to be profitable? Because it's just the right thing to do.
Yeah.
Like our contrails or our green light work, I think we don't really worry about that. It's just the right thing to do for the planet.
Yeah.
Or a lot of the healthcare related work we've been doing in developing countries, I think is low and middle income countries. We've deployed some, retinal image based machine learning systems to help with diagnosing diseases like diabetic retinopathy in partnership with, eye hospitals in India or in other locations. And I think that's a pretty good thing to be doing, regardless of whether that's profitable or not. In other areas, we think there's really important uses of AI and machine learning, and they provide economic benefit, and we create, business models around that. So like some of our cloud-based AI products, people pay money to use them because they're useful, and that's fine. So I think getting that balance right is an important thing, but, it doesn't have to be an either or.
There was an announcement today with respect to the leadership of one of the AI players.
Oh, yeah.
Right? Without mentioning names, I want to put that in the context of what I want to hear from you in terms of whether this should be open source or closed source for the benefit of humanity for the time being.
For what should be open source or closed source?
AI.
Just in general. Okay. Yeah, I mean, I think it's a complicated question. I think, we've actually had a long history of open source releases of sort of basic building blocks of AI toolkits. So things like TensorFlow or JAX, we've been working on for many years and releasing, and actually huge number of developers around the world have created all kinds of amazing things with TensorFlow. I think, there's 40 million downloads of that system. Wow. Maybe probably more now, that have enabled things like the cassava detection example I mentioned. At the same time, I think the most capable models, I think it's really good to make sure that they are deployed in a safe manner. And when you completely release the model to the world, it can have all kinds of amazing uses, but it can also be used in ways that maybe are, less desirable. And you don't really have control of that. That doesn't mean we shouldn't open source models. I think it's a balance, right? Like we want, amazing models that are open source that people can do all kinds of good things with. Right. But the most capable models, I would be a little more circumspect. You can offer API access to people, and they can build things on top of that. But that doesn't necessarily mean that we want them, to be completely open and available.
China is a large population, right? If you hear some of the experts on AI from China, they seem to think that they're going to be ahead of the United States in AI because they've got more data points. Is that the right logical way to think about how AI is going to move forward, or there are other variables that need to be taken into account?
Yeah, I mean, I think obviously AI is being worked on all across the world,
right,
including in the US, including in China,
yep,
many people in Europe, and all over Asia and Southeast Asia.
Yep.
I think it's a technology that is very relevant to many, many things, and so it's natural that there's lots of work on it everywhere. I mean, I think it's not so much about getting ahead. It's about everyone working on, improving the capabilities of what these systems can do, making sure that they are deployed in ways that benefit people, citizens, or, users of the company's products, or, improving the lives of patients or clinicians. There's a lot of things that can be done with AI. And, I think having a responsible approach where you're looking at the ways in which this technology is being used and deployed and contemplating how it should be used in the future is a really helpful thing.
If you take a look at some of the reports on the value proposition coming from AI, right? I mean, some pontification might say it's going to be between $50 to $100 trillion worth of economic value in the next 10 to 15 years, right?
Right.
I come from a developing country, and you've grown up in some developing countries, right? In Africa and all that, right? It just seems, from an intuitive standpoint, that most of the value is going to accrue to just the United States and China, right? I mean, this is coming from me, right? My perspective, right?
Yeah, sure.
I want to hear, what your views are with respect to how people in Southeast Asia could actually feel confident about being able to capture a little bit of that value proposition, which could amount to $50 to $100 trillion, globally speaking, in the next 10 to 15 years.
Yeah. I mean, I think...
What do we need to do to make sure that we're relevant, that we're participatory in this narrative?
It's actually a really good question. I mean, I think the sort of increasing interest in AI and machine learning is something that I think you want to encourage people in, your country and other countries to learn about these technologies, to identify ways in which they can be applied by local companies, by local, universities and people, developers in your country. I think that is a way to make sure that everyone participates in what is the potential, benefits of AI, both kind of societally, but also economically.
You were asked this at the TED Talk. I'm going to ask you again. How do you make sure that you're going to carry forward the pre-existing negativity into the future?
That we don't carry forward that? Yeah. In terms of
well, I mean, inherently there's something that's negatively biased, right?
Yeah.
With a pre-existing technology, right? What do you do to make sure that that's not carried forward?
Yeah, I mean, I think
with respect to what's good for humanity, with respect to what's good for the community and the person and all that stuff.
Yeah, I mean, I think this is definitely one of the risks of AI and machine learning is these systems learn from observations about the world.
Right.
And if they observe the way the world works and we are unhappy with the way the world works in certain ways, these systems will learn to replicate that behavior and maybe even accelerate it, because now you can have an automated decision about, as one example, who should get a home loan or not. We know, those are not always based entirely on fair decisions. They're sometimes biased in various ways by, human fallibility. And that can be perpetuated if you train a machine learning model on biased home loan decisions. You will now have an automated system that makes biased home loan decisions. So there's a lot of work on how do you take data that itself is biased, make sure that you can correct a model so that it doesn't have that form of bias, but it does have, other kinds of properties. A lot of these things are learning statistical associations between things, and some of that bias is completely appropriate. Like if you want the model to know that the word purr is associated with cat, right? That's biased,
Purr,
but it's
P-U-R or
P-U-R-R, like, but that's not a bias we're particularly concerned with. But there are biases in the model about, who gets a home loan that we are concerned with. And I think this is partly harkening back to how we think about things in terms of our AI principles. You want to be looking and avoiding harmful or unfair bias.
Right.
And that there's a whole, a lot of those problems and things that we list in our AI principles, some of those are active areas of research where, we have some techniques that can eliminate bias or reduce bias, but not completely solve the problem. And so we want to continue to make sure that we do cutting edge research on those areas, but also applying the best known techniques that we have now to, the problems at hand for today.
Last question on AI. How do you see it from a policy-making standpoint? I mean, I get the sense, again, as a layman, that the technologists are way ahead of the regulators in many countries around the world, right?
Yeah.
And I think it's in your long-term interest to make sure that there is an alignment, right, of wisdom, knowledge, and being informed, right?
Yeah.
How do we align these two? It gets even more interesting in a developing country, much less underdeveloped country. Right? How do you see that going forward?
Yeah, I think in general, the field of AI has been moving very fast, and that's generally kind of at odds with careful, deliberative processes that are often inherent in politics and regulatory, decision making. I think it's really useful for technologists to help inform policymakers about what is currently possible, what is likely to be possible 5 years from now, what is likely to, what are potential paths 5 and 10 years down the road, so that they can be informed and make good decisions about, okay, we should regulate this kind of thing in this way, maybe we shouldn't regulate this other, potential application. I think, I often think of these in terms of the actual application of AI, because it's a very broad technology. And so what is appropriate in one setting may not make the most sense for another. And often there are kind of regulatory frameworks in particular domains that already exist. And with some, modest changing or informing about how AI could be used in that domain, that regulatory framework can be, modified, but not completely overhauled, right? Like I think healthcare is a really good one. Most healthcare, there's a lot of healthcare regulations in lots of places in the world. And, now AI is being applied to some kinds of diagnostic approaches. But, regulators already exist in those domains and are thinking about these issues. There's other things which are like completely new domains that AI enables where there isn't sort of an existing regulatory framework. And I think it makes sense for policymakers to take a look at, okay, well, what does this technology do? What can it do? What sorts of harms might exist that could happen that might, hurt our populations or people, and what do we want to do about it? But what I also think it's important to look at, how do we not hamper the potential of some of these approaches, but still protect, the public interest from from harm of various kinds.
Jeff, are you getting the sense that you're not recruiting good engineers as fast as you want? Or are you getting the supply of good engineers at the right pace at Google?
Yeah, I mean, I think it's a good question. I think one of the things that this shift to much more focus on AI and machine learning in computing in general over the last decade or so what has happened is 10 years ago, machine learning was one thing that some people emerged from university with a little bit of understanding of, but not everyone. What I think has happened particularly from like a computer science program is what I'm talking about. I think what's happened over the last decade is there's been such interest created in what can these technologies do that universities are really reacting to this. And so now it's pretty hard, I think, to emerge from a undergraduate program with, without having at least taken a machine learning course or being exposed to it in some way. And I think that's helpful because now we have more people who understand this technology, at least somewhat, and, can understand, some of the potential harms that can result from applying it, the basic techniques, the kinds of things that are possible now, the kinds of things that are, not quite possible, but are likely to be possible. And the field is moving fast. So you want people to have that understanding and then also kind of keep up with the changes in what is possible.
We've talked a little more than an hour. I feel like I've just taken a semester's worth of computer science class.
Okay.
It's hardcore, man. I mean, you strike me as a hardcore scientist, right? But just personally, what do you do to chill?
Oh, yeah. I mean, I love hanging out with my family. I have two wonderful daughters who are now adults.
You sound like you have cats because you talk about cats all the time.
No, I used to have cats. I no longer have cats.
Okay.
Part of the reason we talk about cats is we were doing some unsupervised learning ages ago. Basically, we took 10 million random frames from random YouTube videos, and we trained a neural network without any labels. So the kinds of patterns the system would learn to pick up on. And then we sort of said, what does it learn to identify? And since it's YouTube, one of the things was cats. So we had a particular neuron that would fire when there was a cat face in the image, even though it had never been told what a cat is, which is kind of cool. It's sort of like how humans learn, right? It's a very unsupervised thing. You're mostly just taking in the world as a young child. And then you get an occasional bit of supervision. You're like, okay, that's a cat. And then the young child associates, the kind of vague patterns they've learned to build up about, what constitutes a cat with the word cat. Anyway, sorry, that was a bit of a digression.
Having been born in Hawaii and having grown up in Africa and all the other parts of the world, any outdoor stuff you do?
Oh yeah. So I also, I like to do various kinds of exercise. So I play in 2 different soccer leagues. I'm clinging on in the 25 and over A division of my leagues. The 25-year-olds seem faster every year, which is annoying. And then
I got to ask you, Ronaldo or Messi?
Oh, Messi. Sorry, Ronaldo.
Oh yeah. I'm with you.
Yeah.
I'm with you.
Yeah. Particularly peak Barcelona Messi. It was like,
and the World Cup too.
Yeah, and the World Cup. I'm glad he won the World Cup.
That was awesome.
It's great to see because he's clearly the best player in the world, and it was nice to see him win a World Cup.
Jeff, thank you so much for your time.
Sure.
You've been kind.
Thank you. Appreciate it.
Thank you. That was Jeff Dean, the chief scientist at Google. Thank you.